So let us discuss about elimination reactions. A specific kind of elimination reactions which is elimination unimolecular reaction or E1 reaction. As the name suggests, elimination reaction is a reaction where one part of the molecule will be removed from the molecule or will be eliminated. To understand, to understand this specific kind of reaction, we will take an example of a specific reaction which is acid catalyzed dehydration of tertiary butyl alcohol. So this is the tertiary butyl alcohol, and this reaction happens in three steps. The first step is the protonation of the hydroxide group and the formation of a positively charged ion. And in the rate determining step, this positively charged ion will remove the H2O molecule, one molecule of H2O, and will form a carbocation. This is the slowest step of the reaction, and hence this is the rate determining step. And as we can see, the name of the reaction is elimination unimolecular or E1. This number 1 suggests that the slowest step of the reaction will involve only one molecule. Here we can see that step number 2, which is the slowest step of the reaction, involved only one molecule. Hence, uh, this is a unimolecular reaction. And in the final step is the formation of the alkene, where the proton will be taken away by a water molecule. A water molecule is acting as a base here and giving you the product alkene. So as we can see that in this reaction, carbocation is formed in the rate determining step. So we can also say that the stability of this carbocation will determine the overall rate of the reaction. So, so if we can, or if a more stable carbocation is formed during this reaction, then the reaction will go faster. So, as we know that tertiary carbocations are much stable compared to that of secondary or primary carbocation. So if we check the energy profile of these three kind of carbocation, we will see that a very less amount of energy is needed to form a tertiary carbocation from a tertiary butyl alcohol or any kind of tertiary alcohol or 3-degree alcohol. Whereas in case of 2-degree alcohols, a little bit more energy is needed to form the corresponding carbocation. And in case of primary alcohol or 1-degree alcohol, a very high amount of energy is needed to form the primary carbocation, which means that E1 reaction in with a primary carbon or a primary alcohol is kind of impossible because the very high amount of energy needed to form the intermediate carbocation. So this is the reason that tertiary alcohol generally undergo E1 mechanism to form a elimination product, whereas primary alcohol doesn't go. And as I have said that there is a possibility of carbocation formation during the reaction, so there is always a possibility of rearrangement. What is that? So to understand the, the scenario where a rearrangement may happen, we have to take a specific example, and this is the compound which I am going to take. In this case also we will discuss acid catalyzed dehydration reaction. Here also we have a hydroxide group, but in this case the hydroxide group is attached to a 2-degree carbocation. Sorry, not carbocation, but 2-degree carbon. Also, if we check very carefully, we can see that there is another 3-degree carbon nearby. So, when the reaction will proceed, the first step, the alcohol, the 2-degree alcohol is going to take the proton from the solvent and will form the OH2 plus. And now in the next step, of course, the H2O will come out of the system and will produce 2-degree carbocation. But as we know that 2-degree carbocations are not very much stable or not stable compared to that of a 3-degree carbocation. So what will happen? rearrangement will go on. So the methyl group which is near will shift to this carbon, and as a result we will get a 3-degree carbon or 3-degree carbocation, which is much more stable compared to this 2-degree carbocation. So this 3-degree carbocation will form through a rearrangement because this will stabilize the system. And now as we have a 3-degree carbocation, now the reaction can go forward to give the product alkene. But here also we have uh, a little bit confusion. This is not a confusion in the term of science, but here we can see that two protons are there, and the H2 molecule which is acting as a base here can take any of these two protons, and if it takes this proton which is marked in blue, it will give this specific alkene. And if this proton which is marked in orange here, if this is taken by the H2 molecule, then we will get this product, the product which is drawn with a orange ink. But now we have to compare the stability of this product. As we know that the product which is much more substituted, the product alkene which is much more substituted is more stable. So we can say that this second alkene is actually the major product of the reaction, whereas the first alkene, which is not that much substituted, so this will be the minor product of this reaction. And why is it so? Why this alkene is minor? Why the second one is a major product? Or why the first alkene is less stable compared to that of the second alkene is described in my previous video, and of course I'm going to describe it again in a short video, in a single short video later on. Thank you for watching.